Hello everyone. Welcome to the live section of this course, which is Foundation of Classical Electrodynamics. I'm Gitanjali. I'm a merit scholar from IIT Delhi, and I'm the TA for this course. And as I have said in our previous live session, the purpose of this live session is to go through the concept that has been taught during this week and to solve few numerical problems or conceptual problems that can help you to solve the assignment as well as your conceptual clarification. So now we are in week 10. So in week 10, we start mostly discuss about what is the magnetic flux and what is Faraday's law. Then we discuss what is the energy associated with the magnetic field. Similar to the electrostatic case, in here also we have magnetic energy that can be stored due to a magnetic field. And lastly, we discuss about Maxwell's four equation, which relate the electric field with the magnetic field. So electric field and magnetic field, these are not completely independent. They depend on each other, and Maxwell's equation shows how they are related to each other. So let me give a um, uh, brief summary of what you have seen in week 10. So after that, we'll start solving the problems that is related to the week. So if you recall, in electrostatic case, we have divergence of, sorry, curl of E is 0. So this is one of the fundamental equation for the system to be electrostatics. And from this, we conclude that electric field is a conservative field, and we can write electric field in terms of some gradient of a scalar function, which we call as electric potential. So for electrostatic case, you can write E in terms of a scalar potential. But if you, this is for the case where the source charge is at rest. The test charge can be moving, but the source charge for which the electric field is present there, so it should be at rest. But if you consider a case where the source charge is moving as well as the magnetic field that is created by this source charge is not constant. So in that case, we have curl of E, it is not equal to 0. And to be exact, the curl of E, it can be, you can write it in terms of negative of gradient dou B by dou T. So this is Faraday's law. It's like a conservation of energy. If you recall, the it is related to the flux, and the negative sign it indicates that it approaches the flux for which the magnetic field is either increasing or it can be decreasing. So curl of E in this case, you can write it as minus of dou B by dou T. And divergence of B is always 0 from that. If you recall, using this relation, we conclude that you can write B as some curl of a vector function. Because the divergence of gradient is always 0, it's a mathematical definition. It's a mathematical properties. So if you put this here, so we have curl of A should be 0. So from this, if you rearrange it, so we have curl of E plus dou A by dou T is 0. So instead of curl of E 0, we are having an additional term which is dou A by dou T. So that means you can write the whole expression in terms of some gradient of some scalar function. Let's say it is gradient of phi. So that means for this case, we can write the electric field in terms of a scalar function as well as a vector function. Okay, so this is the complete expression of electric field when we don't have any electrostatic case. So after that, what we have seen similar to the electrostatic case, where we have where we have defined the electric flux. So it is nothing but the number of electric field lines that is passing through a surface. So similarly here also, we have magnetic flux. So you can write it as BDS, phi m is B integration of BDS. And because when the magnetic flux it changes with respect to time, then for that case we can have a induced EMF, which is nothing but this is induced because to change the cause that is changing the magnetic flux. So induced EMF is nothing but negative of d phi by dt. Okay, so and we have also seen one special case of Faraday's disk generator. So for that case, you can also write induced EMF in terms of B dot dl cross B. And using this relation, we find out that the electric induced EMF for this case, for the Faraday's disk, you can write it as half omega P a square. So this is about the flux. Now, one of the property of a circuit or any coil that if the source is changing, then there will be one opposition. So to define that, you can use. We often use either self-inductance or when we have two interacting system. In that case, we have mutual inductance. So this self-inductance, it is related to the flux that is changing. So phi b, it's directly proportional to I. That means phi b is Li. So proportionality constant is the self-inductance. And if you put the relation, you can also rewrite the induced EMF as minus of L di by dt. So these are the relation that you can that you should know to solve the problems. And in mutual inductance, we have more than one interactive system. And because of the change in the flux in one, there will be induced EMF in second. Or if the flux is changing in one, then there will be induced EMF in first case. So this is for to define the system, we often define mutual inductance. So phi 2, the flux through the coil or loop 2, it is directly proportional to the current through the first system or the first coil. So that means you can write phi 2 as M21, phi, or it should be I1. And similarly here, phi 1 is directly proportional to I2. And we have phi 1 is M12, I2. After that, we explicitly saw how we can for a two arbitrary coil, what will be the general expression for a mutual inductance. So M21, if you recall, it is given by Newman's formula. It is mu naught by 4 pi double integration dl1 dl2 by r. So, and this indicates that the mutual inductance, it does depend on the geometry of the object, like the shape of the object or like the size of the object. And it also depends on the position of these two objects. Okay. And we have also seen what is the expression for the magnetic field energy, which is nothing but 1 by 2 mu naught b square dv. Okay. After that, We define the Maxwell's equation. We saw what are the four crucial equation of Maxwell's. So first one is electrostatic case. The Gauss law for electrostatics. So this is divergence of is rho by epsilon naught. So this will give the electric flux. We recall E dot ds is q enclosed by epsilon naught. This you can easily derive from this first equation. And for the second case, it basically it tells that magnetic monopole doesn't exist. So whenever you have a north pole, you will also get a south pole. So divergence of B is zero. And one thing we deduce from here is B. You can write it as some curl of some vector potential. Third is the Faraday's law. That is, whenever there is a change in magnetic field, there will be an electric field associated with it. So the change in magnetic field will create a electric uh, electric field, and if the circuit is closed, then we'll also see a current through this flow. So this is Faraday's law. And the last equation is the opposite of the third equation. That is, whenever there is a change in electric field or whenever there is a current, so we will have a magnetic field. So initially, the Maxwell's equation is like divergence of B is mu naught J. But so this basically tells that whenever there is a current carrying wire or whenever there is a current carrying loop or any current source, there will be a magnetic field there. But if you put some mathematical algebraic equation like the divergence of curl is always zero. So this we know that divergence of B is always zero. So, but if you see the right hand side, the divergence of J is not always zero. So it is always zero whenever we are considering the magnetostatic case. So to reformulate the Maxwell's equation, we know that the divergence of J plus dou rho by dou t should be zero. So that means there should be a dou rho by dou t term in the final fourth equation. That means, and to rewrite in terms of electric field, one thing you can do, you can write this is rho by epsilon naught. And if you recall the first equation, this is nothing but divergence of E. And we can also put dou by dou t to, we can take it to inside. So this will give epsilon naught divergence of dou E by dou t. So that means in addition to this term, we should have epsilon naught dou E by dou t so that the right hand side should match with the left hand side. So this new term, it is known as the displacement current, and it is due to the change in electric field. So the complete equation that we'll get is divergence of B should be mu naught. You can write JC, conduction current, plus mu naught JD. This is the displacement current, which is epsilon naught dou E by dou T. And according to this, the Ampere's law will also modify. Initially, we have B dot dl is I enclosed, but now we'll have I total, which is due to the free current as well as due to the displacement current. So these are the modification that has been introduced by Maxwell's. So now we'll see the problems that is related to Maxwell's equation, self-inductance, mutual inductance, as well as the flux. So let us start with our first problem. So it's one of the conceptual problem. So for a identify the statement that is not true for the ferromagnetic material. So first option is they have large chi-m, which is true because these are highly magnetic materials. So magnetic susceptibility should be high. Second is they have a fixed value of mu r. So it is not true because depending on the material, depending on the magnetic material, maybe iron, cobalt, or nickel. So they have different value of magnetic properties. So they should have different value of mu r. So that means the second option is not true. And let us see the third option also because it may happens in a question there are more than two solutions. So always check that so that you can confirm yes, the second option is wrong. Second and also any other option is right or wrong. So in third, energy loss is proportional to the area of the stress slope, which is also true. And the third is they lose their non-linearity property above a Curie temperature. So this is always true. So that means the answer to this option is B. Okay. So this is related to the conceptual. Let us see the next problem. For the second problem, we have consider a ferromagnetic material with permeability mu is 4.5 mu naught. So there is a ferromagnetic material with mu is 4.5 mu 0. Magnetic induction is B, which is 4y zk into 10 to the minus 3 Weber per meter square. So for this case, find out the magnetic field intensity, which is the external magnetic field. What will be the magnetic field for this case? So this is quite straightforward. You just need to recall the what is the relation between the magnetic flux and the given parameter. So if you recall for a linear material, you can write B is mu h. That means h is B by mu. B is given to us. It is 4y z cube into 10 to the minus 3. Mu is 4.5 mu naught and mu naught value is 4 pi to 10 to the minus 7. So if you simplify it, you will get the value around 707, 707.3 y z cube ampere per meter. That means the magnetic field intensity is option B. For the second case, what we have, we need to calculate what is the magnetization M of this ferromagnetic material. So recall that we can write P is mu naught H plus M. So this is the general equation, whether the magnetic material is non-linear or non-linear, it is always valid. So from this you can write M is B by mu naught minus H. And B you can write this is mu H for the linear material. So that means this is mu by mu naught minus 1 H. The value of H we have already calculated it in the previous session, previous problem. So mu is also given, it is 4.5 mu naught. minus 1 and H is 707.3. So this will give 3.5 into 707.3 and this will give 2.476. Direction is Y, ZK, kilo ampere per meter. Option C. Okay, so the last problem for question number 2 is to find out what is the bound current density, JB. So JB, if you recall, it is nothing but curl of M. M we have already calculated in our previous problem. So this will come out as D and Z by dy xk. So this there will be a y here. So this will give 2.476 xk kilo ampere per meter square. So that means the answer should be option A. Okay. So let us move to our third problem. It says there is an oscillating voltage Vt, which is V0 cos omega t. It is applied across a parallel plate capacitor having a plate separation on D. So find out the displacement current density through the capacitor. This is also straightforward. You just need to recall what is the expression for the displacement current density. And this we have seen in our introduction part. So JD, you can write it as epsilon naught dou E by dou T. Or in terms of voltage, you can write this is epsilon naught. E is V by D. So this is dou V by dou T. So epsilon by D, dou by dou T of V is V0 cos omega T. So epsilon naught V0 omega by D. There will be minus sign sine omega T. So the answer would be option B. Okay, so let us move to our next problem. So I will give you some time to calculate it. Let me first read out the question. So there is, you need to calculate what is the EMF induced in a stationary circular loop of radius r in a time varying magnetic field BT. It is given BT is B0 cos omega t. And it is changing with time because it is a cos function. Uh, then find the induced EMF in a circular loop. Calculate it. Okay, so it is related to the magnetic flux, change in magnetic flux. So E is, you can write it as minus of dou phi B by dou T. So it's a circular loop. That means area you can write it as pi r square. And the area is not changing, only the magnetic field is changing. So that means you can take out the area pi r square d by dt of B0 cos omega t. So this will give B0 pi r square omega. Cos will give minus of sine omega t. So answer would be option D. Okay, so for the fourth question, it's asking which one of the following expression represent a electric field due to a time varying magnetic field. So for this, what you can check. So the magnetic field is changing with respect to time, right? So that means if you recall the Maxwell's third equation, that is the Faraday's laws. So curl of E is minus of dou B by dou T. That means if it is a time varying magnetic field, curl should be non-zero. So the question you can guess it is indirectly asking which one of the following is not the case for the electrostatics, because for electrostatics we have curl of E is zero, and it is asking there is a time varying magnetic field, so that means the curl of E should be non-zero. Let us check one by one. For first option, we have Ex is Kx, Ey is Ky, Ez is Kz. So curl of V for the Cartesian coordinate is K, Y, K, Z, K, dou X, dou Y, dou Z. And this is, we can take out the K, this is X, Y, and Z. And if we check the curl, I think it should be zero. So this is zero. So that means it's a case for electrostatics. The magnetic field is not changing with respect to time. So for the B part, we have Ex is X, Ey is minus Y, Ez it is zero. So curl of E, it is also zero because it is somewhat similar to option A, but only the thing is Ez is zero. X cape, Y cape, Z cape, dou X, dou Y, dou Z, X minus Y, 0. So this will also give 0. Third option, you can easily guess it is also 0 because it is similar to the option A, but only the difference is there is a minus sign here. But it doesn't depend on the sign because it depends on what are the coefficient here. So answer would be option D. So but first let us check whether we are getting the non-zero curl for this case. Ex is ky, ey is minus kx, and ez is 2z. The curl of E is We can't take out K now. So this is K or escape Y cape Z cape does do Y do Z KY minus K's do Z. Okay, is there here also. So I think we can take out the K for all the coach. Now if we check the X part, it is 0. Y part, dose of 2Z 0, dose Z of Y 0. And Z part, for Z part, this is non-zero. This will give minus 2. Minus 2 K ZK. This is non-zero. That means it is corresponding to a time varying magnetic field. So answer would be option D. Okay, so for question number 6, there is a time dependent magnetic field BT, which is produced in a circular region of space. So there is a time dependent magnetic field PT, which is produced in a circular region of space infinitely long and of radius r. The magnetic field is given as B, it is given as B0 T ZK, and it is 0 for r greater than r. So it is non-zero when r less than r and 0 when r greater than r. B0 is a constant. So you need to find out what is the electric field at a point r equal to 2r. Let us see how we can solve it. So to find out the electric field, if you recall the Faraday's law, it is relating whenever there is a change in magnetic field, there will be electric field associated with it. So we need to use that equation. So curl of E is minus of dou V by dou T. Or you can also rewrite it as E dot dl is minus of integration of dou V by dou T of dA. This we have already seen. So let us solve it. So dou by dou T of B is given B0 T ZK dot dA. So B0 is a constant. Dou by dou T of T will give 1. This is ZK dot dA. And it's given it's a circular region and the field is only non-zero within the radius r. So that means the flux should be integrated from 0 to r. So this will be B0 pi r square. So that means E 2 pi r. This is B0 pi r square. Or E, this should be minus B0 r square by 2r. And the question is asking what will be the electric field at a distance r equal to 2r. So we just need to put the value of r. The electric field is minus B0 r square to 2r. So this will give B0R by 4R by 4. The direction will be in theta cap direction. If you want to see, this will be the total expression. So answer would be option B, minus B0R by 4 theta cap. Okay, so let us see question number 7. For question number 7, we have a circular conducting ring of radius r, which rotates with a constant angular velocity omega about its diameter, placed along the x-axis, and there is a uniform magnetic field B applied along the y-axis. If at time t equal to 0, the ring is entirely in the xy plane, the EMF induced in the ring for time t greater than 0 is. So I would like you to solve. Let us try first, then let me know whether you are getting the answer or not. And if you are getting stuck, let me show the steps. Let me reiterate the question. So there is a circular conducting ring of radius r, which rotates with constant angular velocity omega about its diameter. So this is along x, this is along y. And there is a uniform magnetic field B along the y-axis. So B, it is uniform. We can take B0 y cap. And at time t equal to 0, the ring is entirely in the xy plane. So what will happen when you rotate it, and what will be the EMF induced for time t greater than 0? Option D. Option B. Okay. So let us check then. So it's given that it's time t equal to 0, it is completely in the xy plane. That means n cap is the area vector of the unit vector along the area vector, or this circular is along the z cap direction. So n cap is z cap. And when you rotate it about the x-axis by an angle theta, of which we can write it as omega t. So that means n cap will change. So it will have component along z direction as well as along the y direction. So that means n cap you can write it as cos omega t z cap plus sine omega t y cap. So this is why I'm writing, because if you put theta equal to 0 here, you can get n cap is z cap, which is for time t equal to 0. It is completely in the xy plane. So that is why the n cap should be written as like this, not the sine function here, not the cos function here. So cos function should be associated with z cap, so that when t equal to 0, n cap is z cap. And when t is not 0, this is the complete expression. So now let us, it's given b is b0 y cap. So that means the flux associated with this is b dot a, b is b0 y cap, and a is a and cap. So the dot product, it will pick out the y cap component. So that means it will give B a cos, not cos, sine omega t. And the area vector for this circle is pi r square. So that means the flux, the induced EMF is negative of d phi by dt, which is d by dt of b0 pi r square sine omega t minus b0 pi r square omega, and sine will give a cos omega t. So that means the induced EMF. So negative sign only indicates that it opposes the flux. So if you take the magnitude, the EMF induces B0 pi r square omega cos omega t. So this is option D. Okay. So is this clear? Okay. So let us move to our next problem. So there is a square loop of side A which lies on a table at a distance s from a very long straight wire. So let me draw it side by side. So there is a long wire which carries current I, and there is a square loop. Side is A, the distance is. Find the flux of B through the loop. First is you need to find out the flux. Then in second case, if someone now pulls the loop directly away from the wire at a speed v, then what is the EMF induced? And in what direction, either it is clockwise or anti-clockwise, and does the current flow? And in C option, we need to find out what is the induced EMF if the loop is pulled to the right at a speed v. So finding out the first answer is quite easy, and it has been, I think it's been solved in the lecture. So let me quickly go through it. So to find out it, what is changing here? The magnetic field is changing here. If you recall, for a infinitely long wire, you can write B is mu naught I by 2 pi x. Direction is phi cap direction. So because there is a square loop, the perpendicular distance, this distance is changing. Let us say it is at a distance x. We are considering a region dx. So we want to find out what is the flux through this shaded region. So flux is BD is mu naught I by 2 pi x Okay. And dA is, what will be dA? Direction of B and the area vector is in the same direction. So dA is dx into A, A dx. Okay. So this will give mu naught I A by 2 pi dxx. So x will vary from s to s plus a. That means this will give mu naught I by 2 pi ln s plus a by s. This is the flux. In the second part, we are pulling the square loop away from the uh, pi. So that means there will be a change in magnetic field and there will be a change in flux, and the change in flux will create a induced EMF. So induced EMF is minus of d phi by dt, d by dt of mu naught IA by 2 pi ln s plus a by s. It is take out the constant, and this will give ln a is 1 by a, or ln x is 1 by x. So this will give s plus a by s, and we have d by dt of s plus a by s, which is 1 plus a by s. Not I by 2 pi s by s plus a. This will give minus of a by s. 1 s will cancel, and there will be a ds by dt, which is nothing but the velocity, right? Minus mu naught I a square by 2 pi s plus a, and we will have 1 is here plus v. Can you tell me what will be the direction of current? So if you are pulling the square loop away from the y, so what will be the direction of current? Negative x. Yes. So it should be counterclockwise. If you, so if you pull this, then the flux will decrease. And in which direction it decrease? In the upward direction, it is decreasing. So that is why the flux of the current should be such that it will oppose the decrease in the flux. So that means the current should be in the counterclockwise direction. Okay. So for option C, can you let me know the answer? So if you, instead of pulling away from this loop, now we are pulling the square loop parallel to the wire. So what will be the flux or the induced EMF? Let me know the flux first. Or instead of flux, let me know whether there will be induced EMF or not, and what will be the value for induced EMF. There won't be any change in flux. Yes. Okay. So the guess is correct because we are moving parallel to the wire. So the magnetic field won't change. Uh, Whatever we have calculated, the flux won't change. So that means induced EMF should be zero for this case. So for option C, there will be phi is constant and the induced EMF is zero. Okay, good. Let us see our question number 9. So it says there are two infinite parallel wires separated by a distance d, which carries equal current I in the opposite direction. So let me draw it side by side. So there are two infinitely long wires separated by a distance d, carries equal current in opposite direction. Let us say this is I. So this picture is already given in the question. I forgot to include it. So this is in positive direction, this is in negative direction. And the current is increasing at a rate of di by dt. There is a square loop of wire length d on a side lines in the plane of wire at a distance t from one of the parallel wire. Okay, so let me show the figure first. So this is square loop is the distance t and the sides of this square loop is also d. So for this case, find the first option is find the EMF induced in the square loop, and B is the induced current is clockwise or anticlockwise. Justify your answer. So first we need to calculate the EMF first, which is quite easy because we know how to calculate the magnetic flux due to infinity wire or a square loop. So let us quickly solve it. So there will be uh, because of wire 1, we'll have a flux on square loop, and because of wire 2, there will be a flux on the square. And this flux, if you see, the current is in the opposite direction. That means the flux direction is opposite. So for the general definition of flux is B dot dA, and B for a infinitely long wire is mu naught I by 2 pi r pi k. Or if we are considering this is out of the plane, we can write it as z cap. So that means for the wire 1, the flux is phi 1 and this is BdA. B is mu naught I by 2 pi r dr. Mm, and there will be a D, right? So it's like we are considering a distance or there is dr. The area vector will be d into dr. So this is mu naught I by 2 pi d dr by r. And the r for the first wire, it will vary from what will be the lower limit? It is 2d, right? This is 2d and the maximum distance is 3d. This 2d to 3d. So that means this is mu naught I d by 2 pi ln r. So this will give ln 3 by 2 pi 2. Okay, so this is for the first wire. For the second wire, this is phi 2, which is similar to what we have seen before. The expression should be same. Only the range of the r will change. So we'll get mu naught I d by 2 pi dr by d. And the range of, dr by r. And what will be the range for the r? It is d to 2d. Yes. So this is mu naught I d by 2 pi ln 2. So we have calculated the flux. Now to find out the EMF, we need to calculate the change in flux. So if you see the flux is in the opposite direction and which flux will dominate, whether it is phi 1 or phi 2, which one is dominating over the other? Ln 2 and there is Ln 3 by 2. That means phi 2 will dominate. So net flux is next flux is phi 2 minus phi 1, which is mu naught ID by 2 pi ln 2 minus ln 3 by 2. This is ln A minus ln B. So this will give A by B, ln A by B, so ln 4 by 3. So now the EMF induced will be minus d phi by dt. That means minus d by dt of mu naught ID by 2 pi ln 4 by 3. Other than the current, all these are constant. If you see the question also, it's given that the I is increasing at a rate di by dt. So I is changing. So that means this is minus mu naught d by 2 pi ln 4 by 3 di by dt. This is the induced EMF. Okay. For the second case, we need to find out what is the induced current, whether it is in the clockwise direction and whether it is in the anti-clockwise direction. So what will be the answer for this? Whether it is clockwise or anti-clockwise. Yes, it's clockwise direction because phi 2 is dominating. We have seen phi 2 is dominating. So that means the flux is increasing in the outward direction. So current should be clockwise so that this flux will be decreased. So answer would be clockwise. Okay, now let us see question number 10. So there is a infinitely long solenoid with n turns per unit length, radius r, and it carries a current IT, which is alpha cos omega t, where alpha is a constant, omega is the angular frequency. So find out the electric field at the surface of the solenoid. It's quite easy. Okay, so let solve it and let me know which one of this following option is correct. Option A, let me see. Leonardo income sign Okay, I think it's correct. Let us see the steps now. So I think you have started with the magnetic field of a solenoid, which is nothing but mu naught Ni Z, and it is zero outside. And for because the magnetic field is changing, there will be a flux and there will be induced EMF and as well as a current, and there is a electric field. So EDL is minus of d by dt of BDL. So d by dt of, sorry, this will be integration. B is mu naught and I T ZK, and dA is 2 pi r dr. The limit for this integration will be from 0 to r because outside it is 0. So, and we can take this to inside minus mu naught and do IT by do t 2 pi r dr. I is given, it is alpha cos omega t. So di by dt will give alpha omega. This will becomes mu naught 0 to r sin omega t 2 pi r t. 2 pi r dr integration will be pi r square pi 2. So 2 will cancel. So this will be pi r square. And in the left hand side, we are considering the surface. So this will be 2 pi capital R omega mu naught and sin omega t pi r square is half mu naught n r omega alpha and omega t, which is option A. Okay, so let us see question number 11. Question number 11 is also quite easy. So there is a circular current loop which is carrying a steady current I. The radius of the loop is R. What is the ratio of magnetic energy density at a distance? R is root 3R2, R is root 15R from the center of the circular loop. So for this case, you need to calculate the magnetic energy density. So there is a circular loop and it is carrying current I, radius is R. We need to calculate the magnetic field, magnetic energy density for R is root 3 root 15. So if you recall the magnetic energy density, it is given by B square by 2 mu naught, right? So that means UB is directly proportional to B square. So for these two options, first we need to calculate the magnetic field, and by taking the square of this ratio, we can find out the answer. So if we recall for a circular loop, and on the axis of this circular loop, the magnetic field, we can write it as B is mu naught I naught square I2 naught square plus Z square P by 2. Or this is smaller for this case, mu naught I naught square 2 naught square. So for this constant, B is directly proportional to or inversely proportional to R square P by 2. That means B square is inversely proportional to R square whole cube. So UB is now is inversely proportional to R square whole cube. So UB2 by UB1, this is R square plus R1 square, R square plus R2 square whole cube. R1 is R3R, so this is 3R square, and R2 is, I think, root 15R, 15R square. So this will give 1 by 4 to power cube. So answer will be 1 by 64A, option D. So let us see question number 12. It's quite easy. So I will like you to solve it first, then I will show you the steps. So there are two identical coils, each with 500 turns. These are placed so that 80% of this flux produced by the one links with the other. If a current of 5 ampere is in coil X produces a flux of 10 milliweber in it, find the mutual inductance. Okay, previous question. Is it okay? You are getting B. Hey, is this formula correct? Have you used this formula? Okay. Then let me see whether I have wrongly calculated in your slide. So R1 is root 3R and R2 is root 15R. Is it B1 by B2? No, it's B2 by B1. Okay, I think you got confused here. But here also we will get 4. It is B2 by B1 to be exact. B2 by B1 square. So you let me see, this will be 3R square, this is 15R square, so this will give 4R square, and this is 16R square. This is 1 by 4, So 1 by 4 to power cube. I think 60, you should get 64. So this is constant, so that's why I haven't included this part. Only the variable is this. And b square will give, so this square will be removed because it is square. Magnetic energy density is square of B. Okay, if you haven't squared this, I think for that case you will get 1 by 8. Yes. Okay. So I hope now it's clear. Question number 11. So let us see question number 12. Solve. So, what is the answer you are getting? So, Dinaka, do you have any doubt? So, is this clear? Okay, so you're getting 0.8 and that's good then. So let us see our next question. Next question is also quite straightforward. So there is a coil which is 50 turns. The current through it changes from 0 to 5 in zero point 0.1 second, and you need to calculate what is the induced EMF. No, so induced EMF is given, it is 2 volt, and find out the self-inductance of this coil. So if you recall, in terms of the self-inductance, you can write is minus L di by dt. That means L is F induced EMF di by dt. So this is 2 and di by dt it is 52.1. So you will get 0.04 Henry. For the 14th question, so there is a figure given. There is a circle and two infinitely wires, infinitely long wires. So in the figure, two conductors of infinite length carry current I. They are parallel and they are separated by a distance 2a. A circular conducting ring of radius a in the plane of parallel wires lies between the two straight conductors, and this is insulated from them. Find the flux through the circular conducting ring due to this configuration. Okay. So to find out the flux, you will need to take a small length element, small area element, and calculate the small infinitesimally small flux there. Then we can integrate to calculate the total flux. So for this case, let us say we are looking at the distance y. or R. The distance R we are considering a portion dr here. Or I think it's better to take it here. We'll see why I'm taking it here. This is dr length. This is the center. Radius A. This is also A. Okay. This is also distance R. That means this distance is 2A minus R. And at this point, what is the magnetic field due to these two wires? If you check, these magnetic fields are in the same direction, so they will add up. So BR, you can write it as mu naught I by 2 pi 1 by R plus 1 by 2A minus R. Let's say this is in the Z curve direction. So now to calculate the magnetic field or the magnetic flux, let us take this distance. This is Y. Let us say this is Y. Current in the opposite direction, but now we are looking at a point in between these two wires, not at a point outside. So in between this two, because the circle is in between these two wires, right? So we are considering a region here, not outside. Outside it will be opposite and flux will be equal. But inside, if you check, they will add up, right? Is it clear now? So we are looking at a point inside in between these two current carrying wires. So if you consider, let us say we are considering a region here. So for this point, because of this first wire, the magnetic field will be in the upward direction, and because of this wire, this will also be in the upward direction. So that means they will add up, not they won't cancel. Is it clear now? Okay, so now we know the magnetic field. So this is the expression. Now to calculate the flux, so that means we need the area of this element. So dr, we know one length element is dr, and now I am taking this vertical distance as a y. So that means the flux through this area of this ring, the shaded area, it is BDS. Or as you can already guess, these two current carrying wire, they will produce the equal flux that will add up. So that means we can take the integration from 0 to a, 2 times of 0 to a BR, and the DS would be area of this shaded region, which is dr into 2y. 4, 0, 2, 3, br y dr. Let us put the values. So br is flux is 4, 0 to a. br is mu naught I by 2 pi 1 by r plus 1 by 2a plus r. And what is y in terms of r and a? So if you see this figure, this distance is y. That means y is square root. Let me draw it properly. So this is the distance y. This distance is r. So this will be a minus r. And this is the radius a. So that means here we can see y is square root a square minus a minus r square. Okay, so this is square root a square minus a minus r. So we are writing in terms of a single variable so that we can calculate the limit of this integration. Now see, let us take this is a minus r is x, or let us take r minus a, it is x. So that means dx is minus dx is dr. I is 4, 0 to a mu naught I by 2 pi. R is a plus 6 plus a minus 6 square root a square minus x square. This is mu naught I 2 by pi 0 to a. This will give, numerator will give 2a, and this is a square minus x square. So we are making this substitution so that we can find out the limit of integration. So this will cancel, this will give a square root. So we have 4 mu naught I by pi 0 to a 1 by square root a square minus x square dx. So this limit of this integration is, we know the value for this integration. It is nothing but sine inverse x by a. So 4 mu naught I by pi sine inverse x by a from 0 to a. So this will give 4 mu naught I by pi. Sine inverse 1 will give pi by 2 and sine inverse 0 will give 0. So we have 2 mu naught I by. So the flux through this circular loop is 2 mu naught I. Okay. So is it clear? Do you want me to jump to the next question, or you need some time to go through the steps? Let me know whether you have any doubt in any of the steps. I will try to clarify it first, then we'll move to the next problem. Vinakar, do you have any doubts? Okay, if not, then let us move to our next problem. So there is a okay. The electric field and the magnetic field corresponding to the scalar and vector potential. It's given the scalar potential is 0 and the vector potential is half kk mu naught a0 ct minus s. These two potential are given to us. You need to find out the electric field and magnetic field associated with this scalar and vector potential. A0 is a constant. Okay. So if you recall, in our introduction part, we have seen if the curl of E is not 0, then we can write electric field is minus of dou A by dou T minus of gradient of this scalar function. And B is, it is always curl of A. Let us see the first one. The scalar function V, pi is V. It is given it is 0. That means we can write E is minus dou A by dou T. A is given, it is half kk mu 0 A0 ct minus x. The time derivative, if you take it, it will give half kk mu 0 A0 c. I think we will get this much. So electric field is this. And now we can easily guess what will be the answer for this because only option C has our correct expression. So no need to calculate B if you want to strictly jump to the answer. But to see it further, we can also calculate B. B is curl of V. A is given, it is in the Z direction. So only AZ is non-zero. Xk, Yk, Zk, Z. Dou X, dou Y, dou Z, 0, 0. AZ is 1 by 2 mu 0 is 0. Ct minus x. And this will give mu 0 a0 by 2 y. Option C. Okay. So let us see question number 16. So there is a small coil of coil 1 which produces a total flux phi total from its winding and 56% of this flux is linked to second coil which and the coil 1 is N1 is 100 tons and N2 is 300 tons. It is given L1 is 2 millihenry. L2 is not given to us and we need to calculate what is the mutual inductance for this case. And it's given the flux created is phi total and 56% of this phi total is linked to the second coil. So for coil 1, what we have, the total flux into N1, this is L1 I1. So that means pi total is for the second one, pi 2 is 56 percentage of pi total. Pi total is L1 I1 by L1. And this we can write it in terms of mutual inductance and current I1. I1 cancel. So M is N2 by N1, 0.56 L1. N2 by N1 is 3, L1 is 2 millihenry. So this will give 3.36 millihenry. Okay. For question number 17, there is a magnetic field B in the Z direction in the region x greater than 0. And it is 0 elsewhere. There is a rectangular loop in the xy plane of sides L along the x direction and H along the y direction. It is inserted into the x greater than 0 region from the x less than 0 region at constant velocity vxk. Which of the following values of L and H will generate a largest EMF? Let us see. Let us draw the diagram first. So there is a square rectangular loop and the length along the y direction is h, along x is L. And magnetic field is present in the x greater than 0 region. So for this case, if you want to write out the flux, magnetic flux, it is BdA, right? So BdA is H and the length segment in the x direction. So in the direction of the x is changing. The length element is changing. So some part is it is gradually entering to this region. Let us say this is x. X part of this length in the x direction. It is present in the magnetic field. So this is BHX. That means EMF induced is you can write it as d phi by dt. Minus pH dx by dt. And dx by dt, you can write it as v, the velocity along the x direction. So induced EMF, it is directly proportional to the h. So it doesn't depend on the length L. It depends on how much of this length is in the y direction. So the greater the value of h, the greater will be the induced EMF. And if you look at the option, this is 3, 2, 6, and 4. That means answer would be option B. So is this clear? We'll solve our last problem for today. So in our last problem, it's given a long uniform but laminated cylindrical iron core of radius 0.1 meter is uniformly wound with wire. So there is a long uniform iron core. This is a radius, it's capital Y, R 0.1 meter. And it is wrapped with wire which excites a uniform flux density in it of BTs. This wire excites B of 1 by pi sine 400t. So first part is to calculate what is the voltage per turn on this wire coil. So voltage per turn, it is nothing but the induced EMF. So V should be equal to the induced EMF, which is d phi by dt. A is constant, it is pi r square. So we can take out pi r square and d by dt of B. B is sine. I have taken out the 1 by pi. This is 400 minus 1 square d by dt of sine. This will give 400 cos 400t. Or if you put the value of r, which is 0.1, so this will give 4 cos 400t. 4. This is the first part. In the second part, we have what is the vector potential due to this core AR at a point r greater than 0.1 meter. So we need to calculate the vector potential now. And if you recall, we have seen one relation between the magnetic flux and the vector potential. So A dl is the magnetic flux, which is BD. We can calculate BDS, and according to that, we can calculate what is the vector potential for a distance. So we are looking at a distance r, which is greater than this radius. So at this region, the flux would be the total flux through this r region, right? So ds would be pi r square. So bt is inside the solenoid, and it is 0 outside the solenoid. So BD is, it is B pi r square. This will be 0.01 sine 400t. Now let us see. So ADL, the line integral of A should be equal to 0.01 sine 400t. ADL will be A 2 pi r. Take it. And this is 0.01 sine 400t. So A would be 1 by 200 pi r sine 400t per meter. In the current direction, let's say it is 5 km direction. So this is the vector potential outside this core. For C option, for the C part, What will be the magnetic field due to this core for a points r greater than 0.1? This you can easily guess because magnetic field outside is 0. So that means the answer for this 0. For the D part, it is quite similar to part B, but only we need to calculate the vector potential inside the core. So only the pi r square will be changed. So calculate it. ADL will be ART to pi r, which will be pi r square B. So pi cancel, r will cancel. ART is r by 2 B, which is pi sine 400t. Okay. So this summarizes what the problems that I wanted to solve in this live session. Let me know whether you have any doubt in any of this problem. We basically solve the problems related to mutual inductance, self-inductance, Maxwell's equation, and the magnetic flux. Dinakar, do you want me to revise any problem or we can stop now? Okay. So for this question, so it's given there is a long iron core and this is a radius of zero point 0.1 meter. It's given. And this iron core is wrapped with wire and this wire excites a time varying magnetic field which is given by BT is 1 by pi sine 400t. So in the first part, we need to calculate what is the voltage pattern on this wire. What will be the, or indirectly it is asking you to calculate what will be the induced EMF. Okay, so find induced EMF on the wire, like on the wire, that means at the surface. So B is given, so induced EMF is quite easy. It is A is pi r square, B is changing. So that means we have taken, this is pi r square, we have taken outside and d by dt of B. So this will give 4 cos 400t volt. Okay. For the second part, for this case, we need to calculate the vector potential due to this core at a distance outside the wire. So at a point here, let's say we are considering a point R here. So to find out the vector potential, if you recall, so this relation we have already seen before in the magnetostatics, right? So ADL, it is related to the magnetic flux. So this we have related to using the I think Stokes theorem. It is call of A ds and call of A is nothing but B. So that means if you know the magnetic flux, then we can calculate what is the vector potential, right? And the direction of vector potential is along the current direction. So current is in the this direction, let's say. So vector potential is also in this direction. It is rotating. And to calculate the magnetic potential, so first we have seen what will be a way where the magnetic flux is non-zero. So BT is only non-zero inside this coil and it is zero outside. So that means we need to take the integration from 0 to R. Okay. So B is a constant and it is only varying with time. So if you take the integration, it will be integration on ds and integration on ds will give pi r square. And You can simplify it. You will get R square will give 0.01. So we will get the magnetic flux as this. From this, I have used the relation A dot dl is the magnetic flux, and dl is nothing but 2 pi r. And from this, you can get A is the this expression. Okay. So finally, we have this. In the C part, what it is asked, what is the magnetic field outside the region for a region greater than R? So, and we know that the magnetic field here is zero. So this is quite straightforward. And for the D part, this is similar to B part, only we need to calculate the vector potential inside this core. So that means now the area vector, it is not capital R square, it is small r square because we are considering a region inside this core. Okay. So the flux should be pi r square B and the vector potential is this expression. Okay. So is it clear now? Okay. So let us meet on next. I think we'll have two more lab session. Then after that, there won't be any lab session. So please try to attend it and let us meet on next Friday same time to solve few more problems. So thank you for joining the session. I hope the problems it will be helpful for you to solve the assignment and for to clarify your conceptual doubts or any numerical doubts. So let us meet on next Friday, same time from 6 to 8. So for now, goodbye everyone.